Everyone. Today we are going to discuss about Johnson's algorithm, an optimized version of Floyd warshall. When we talk about finding all pair shortest path, the first algorithm and the simplest algorithm that comes to our mind is Floyd warshall algorithm, which performs matrix multiplication for path finding. So time complexity of Floyd warshall is order of V cube. Then comes the Johnson's algorithm, which is optimized version of Floyd warshall with lesser time complexity. This algorithm plays a vital role in diverse fields such as network routing, transportation planning, and network analysis. Let's delve into the details of Johnson's algorithm, exploring its significance, working principles, implementation, and real-world applications. Johnson's algorithm for finding all pair shortest path in a graph involves mainly two main steps. Reweighting the graph using the Bellman-Ford algorithm, and the second step is applying Dijkstra's algorithm for each weight. The reweighting process, which we perform using Bellman-Ford algorithm, ensures non-negative weight edges. That is, the value of the new weights must be greater than or equal to 0 because of the inequality. For an edge UV, the potential of V is always less than or equal to potential of U plus weight edge of UV. Bellman-Ford algorithm. Bellman-Ford algorithm is the first step in the Johnson's algorithm. While the process, we will first append the original graph with a new vertex and connect it to all existing vertex with zero weight edges. Then we apply the Bellman-Ford algorithm to compute the vertex potential values of each vertex. Then we reweight the edges of the original graph using the computed potential values by formula weight of UV is equal to weight of UV plus h of V minus h of V. Dijkstra's algorithm. Dijkstra's algorithm is second part of the Johnson's algorithm, and one should have an in-depth understanding of Dijkstra's algorithm in order to perform Johnson's algorithm. In Johnson's algorithm, we apply Dijkstra's algorithm for each vertex to compute the shortest paths in the reweighted graph. Let's take a look at the time complexity analysis. In the worst case scenario, the time complexity of Bellman-Ford algorithm is order of VE, where V is the number of vertices and E is the number of edges in the graph. The time complexity of Dijkstra's algorithm is order of V plus E log V. In conclusion, the total time complexity of Johnson's algorithm is simply the sum of time complexities of running Bellman algorithm for one time and Dijkstra's algorithm for V times, that is, for each vertex one time. Hence, we can say that Johnson's algorithm time complexity is order of V square log V plus V. But take a note that when the graph is a complete graph, then edges are of the order of V square. Then the time complexity of Bellman-Ford algorithm becomes order of V cube, which in turn results in the Johnson's algorithm time complexity of order of V cube, which is similar to Floyd-Warshall algorithm. But in all other cases, Johnson's algorithm is much better in comparison with Floyd-Warshall algorithm with a time complexity of order of V square log V plus V. Now, let us take an example of graph for a better understanding. The first and foremost step of the Johnson's algorithm is to perform Bellman-Ford algorithm, in which the first step is appending a new vertex into the graph and connecting wedges with zero weighted edges. Now, in this graph, you can see the vertex 4 is connected and all the edges connected to all other vertices are zero weighted edges. Now, we will have to calculate the potential values from newly added vertex to all other vertices. Now, here we can see that from vertex 4, we can directly go to vertex 0 with 0 weighted. But for vertex 1, it is minus 5. That is, and in similar way, we will calculate potential values for all other vertices, and the potential values for all other vertices are as. Now the potential values that will be calculated from distance 4 to 0, 1, 2, and 3 vertices are 0, -5, -1, and 0 respectively. Now, the second step of the Bellman-Ford algorithm is to reweight the graph so that all the vertices that are present in the graph, all the edges that are present in the graph will be positive edges. That is performed using a formula weight of AB, that is reweighted weight of AB is equal to weight of AB, that is old weight, plus potential of U minus potential of V. Now let us uh, um, implement this formula for vertex for edge 0, 1. Weight of 0, comma 1 is equal to old weight is -5 plus and the potential value of 0 is 0 minus the potential value is 1 of 1 is -5, which in turns will be equal to 0. Now weight of 1 2 will be equal to weight of 1 or old weight of 1 and 2 h, which is 4, plus potential value of node 1, which is -5, minus potential value of 2, which is -1, which results down to 0. In the similar way, we will reweight all the edges so that all the negative edges present in the graph turns down to positive. Once all the vertices are calculated, we will perform Dijkstra's algorithm on each and every node to calculate the shortest path from each node to another node. In this way, this will be the resultant matrix from from each node to other nodes, finding all pair shortest paths.